Hello, I'm Nicole Hedges. I'm the Associate Lab Manager at the Nanofabrication Facility at North Carolina State University, part of the Research Triangle Nanotechnology Network. In this video, you'll learn the basics of a common nanofabrication technique called chemical vapor deposition, or CVD. Vapor deposition processes are used to deposit thin layers of material, or films, onto a base material called a substrate. These processes, like many other nanofabrication processes, are highly sensitive and must be carried out in a chamber that is isolated from external atmospheric conditions and contaminants at very low pressure inside a vacuum. There are two types of vapor deposition processes: physical vapor deposition and chemical vapor deposition. It's important to be able to distinguish the difference between the two, but for now, let's focus on the core principle of vapor deposition processes. The thin film is deposited on a base material called a substrate, such as glass or silicon wafers. In theory, any material can have a thin film deposited onto its surface. The substrate is essentially a foundation on which we will deposit the thin film. Designing and executing a vapor deposition process requires careful consideration of materials and equipment to ensure compatibility of the system. The substrate is then exposed to one or more vaporized sources. The presence of the vapors, along with other stimuli, will cause a thin film to deposit on the surface of the substrate. The type of thin film that will deposit is dictated by the chemistry of the vapors. Now that you know the basic idea behind vapor deposition, let's talk a little bit about why it's important. Thin films deposited through processes such as vapor deposition have their own unique properties. We may use these films to enhance or improve the original substrate material, or use the film as a component, part of a composite structure. This makes it possible to engineer materials for a very specific application. For example, some films have unique electrical properties. These types of films can be combined to produce microelectronic structures and circuits, such as the microprocessor device shown here. Other films have unique barrier properties, like being waterproof. For example, carbon nanotubes, which can be grown through CVD processes, are extremely hydrophobic. A water drop will bead up and not be absorbed by them, as shown here. These films can be applied to a surface as a coating to protect the material. Similarly, thin films can also improve physical properties, such as making a material resistant to scratching or other physical wear. The properties desired in the final application will dictate the type of film to deposit, which requires careful consideration of the materials and operating conditions for the deposition process. Now that you understand the core concept of vapor deposition and why thin film deposition is useful, let's go over the difference between physical and chemical vapor deposition. In physical vapor deposition, the source is a solid material in solid form inside the chamber with the substrate. Through physical processes, such as heating or sputtering, the solid material forms vapors which will coat the surface of the substrate. Chemical vapor deposition processes are different from physical vapor deposition processes. Instead of forming vapors from a solid material within the chamber, gases are pumped into the chamber from an external source, which react and cause the thin film to deposit. The primary difference between PVD and CVD is the means through which the vapors are generated. In PVD, the vapors need to be generated from a solid or liquid source, whereas in CVD, no new generation is required because the source is already in a vapor phase. There are notable differences, both in deposition and material properties, between films deposited with PVD and CVD. In PVD, the deposition is generally more directional, meaning there is a defined path for how the molecules will deposit onto the surface. This can result in non-conformal films, meaning that the film may not contour smoothly along geometrically complex surfaces, such as trenches or rounded surfaces. By contrast, the nature of CVD processes results in multidirectional deposition, allowing for more conformal deposition along complex surfaces. Now let's go over some tunable parameters within CVD processes. To recap, the substrate is placed in a reactor under vacuum. Source gases are pumped into the reactor, which react with the surface of the substrate. This causes a thin film to deposit on the surface. External stimuli such as heat or plasma can be used to initiate or propagate the reaction, which causes the film to deposit. Gaseous byproducts will form as a result of the reaction and must be pumped out. There are many different types of CVD processes, but they all share this same framework. Within this framework, there is a wide range of variables that can be changed. CVD processes are categorized and classified by conditions used. Let's consider pressure inside the reactor. Some processes are more sensitive and require higher vacuum, while others are not as critical. For this reason, there are different levels of CVD based on pressure. These include atmospheric pressure, low pressure, and ultra-high vacuum chemical vapor deposition processes. Another way to differentiate CVD processes is by the stimulus used within the reactor. Most CVD processes will use heat to help the reaction propagate. However, some samples will degrade at high temperatures, such as polymers or biologic materials. For this reason, some systems use other forms of stimulus. This includes plasma-enhanced CVD, which involves converting the precursors to plasma, and photoinitiated CVD processes, which use UV light. There are also variations on how the sources are introduced, including atomic layer chemical vapor deposition, which introduces the precursor gases one at a time in sequence as opposed to all at one time. This is not an exhaustive list of all types of CVD processes, but these are some of the most commonly used. Chemical vapor deposition makes it possible to produce many modern electronics and advanced materials in a variety of products. CVD is used extensively in the semiconductor industry to make materials used in solar panels, light-emitting diodes, also called LEDs, and integrated circuits used in components found in all types of electronic devices, such as phones, tablets, televisions, and more. CVD also makes it possible to make coatings that make materials last longer, such as making metals resistant to rust and corrosion. This covers the basics of chemical vapor deposition, a versatile fabrication technique used in nanotechnology, making it possible to produce next-gen materials for a variety of applications. Thanks for watching.